This video is a review of the different probability distributions. We'll start first with a random variable because all of the work with probability distributions depends on random variables. So let's consider an experiment of rolling a four-sided die. So a four-sided die, although not very common, is a die that has four sides, and we'll just use it because it's a little bit shorter than using a six-sided die. So here's an example where we want to show the probability distribution. So show it as a table and a graph. So we'll do the table first, and then from the table we'll make the graph. So the first thing that we should do here is define our random variable. So again, the random variable is all of the possible outcomes from the experiment. So if we are rolling a four-sided die, our possible outcomes are 1 to 4. So I'm going to start with a statement here that says let x, our random variable, represent the outcomes of rolling a four-sided die. Whoops. So we'll say the outcomes from a four-sided die. Alright, so our possible outcomes then are, if it's a four-sided die, they're numbered 1 to 4. So 1, 2, 3, and 4. So these are our x values, our random variable values. We'll put a column here for that. The next column, oh sorry about the crooked lines, a little out of practice. The next column is the probability that x equals x. Now this notation is a little bit weird because you're asking what's the probability that x equals x. This is a capital X, and this is the random variable, and this small or lowercase x just represents all the values that the random variable can take on. So in this case, we're trying to find the probability that our random variable x is equal to each of these values here. So what's the probability that x is equal to 1? Well, if it's a four-sided die and we want to know the probability of getting a 1, it's the probability here is just going to be 1 out of 4. And the same is true here. We have a 1 in 4 chance of getting a 2, a 1 in 4 chance of getting a 3, and finally a 1 in 4 chance of getting a 4. So that's the first part of our probability distribution. The last column here is a column for x times the probability of x. In other words, we're going to multiply these two columns over here. Let me just change my pen color. We're going to multiply these two columns over here. So here we'll do the 1 times the quarter or the fourth, and we will write that product over there. I'm going to leave it for now as a common denominator. 1 times 1/4 is 1/4. 2 times 1/4 is 2/4, which I know you know is the same as a half. I'm going to leave it as fourths because that will keep us, that will help us shortly. So we'll get 3/4, and then finally down here we'll get 4/4. Now the reason for doing this column is that if we want to find the expected value, so we use that e at x to represent the expected value. So what this means is that what is the long range average? If we were going to roll this four-sided die over and over and over again, on average what numbers should we get? Well, it turns out that the expected value is just the sum of all of the x times the px's. So that's the sum of this column right up here. So we can add those up. So we've got 1/4 plus 2/4, and you can see now why I didn't reduce the fractions, because if we're going to add these fractions, we're going to need a common denominator anyway. And so we can add those up. 3, 6 plus 4, that's 10/4, which works out to 2.5. So again, if we're to roll the die 1,000 times or 10,000 or 1,000,000 times and take the average, we would expect that we get about 2.5. So that's the expected value, and that's the probability distribution. Now I should note here that this type of distribution is actually what we call a uniform distribution. It's called a uniform distribution because all of the outcomes, all of the outcomes have the same probability. So this is a uniform distribution. Not all distributions are like that. This is kind of a special one. So that's a uniform distribution. So that's the table. Now let's look at the graph. The graph actually just shows this exact same information in a slightly different format. Oh, I should get a ruler or something. That's horrible. Sorry. Let's try that again. That's just not going to cut it. Try that again. A little bit better, maybe. So for our graph, we are going to have the x values along the horizontal axis and the probabilities of x along the vertical axis. So our probabilities here were all exactly the same. They were 1/4 or 25%. So I'm just going to put that here. And our possible outcomes were a 1, a 2, a 3, and a 4. Now these are discrete values. If they're discrete values, meaning they're not continuous, we couldn't roll, for example, a 1.5. So there should be nothing at this part of the graph here at 1.5. So because these are discrete values, we're going to use a histogram rather than a bar graph. So the histogram just has some separation between the bars. So our graph should look something like this. And again, it's not a very exciting graph because it's a uniform distribution. All of our bars should be about the same width. Much easier if you have some grid paper to work with. So there's the probability distribution from there. So following this talk about random variables and whatnot, we moved on to a type of distribution called the binomial distribution. For the binomial distribution, there are trials. Each of the trials are identical, meaning the outcomes are always going to be the same, or the possible outcomes are always going to be the same, and they're independent. The independent part means that one outcome doesn't affect the outcome of the next experiment. So an example of this would be flipping a coin twice. I can flip a coin once and get a head. Whatever happens on that flip doesn't change what happens on my next flip. So when I go to flip a second time, I still have a 50% chance of getting a head or a tail. So that flipping a coin is an example of independent trials, and those trials would be identical. I'm flipping that same coin over and over again. So here we are. We're going to show the probability distribution for the number of threes you get when you roll a six-sided die 4 times. Okay, so our first thing here should be to define our random variable. So the random variable are the possible outcomes, and we're going to let x represent, sorry about my handwriting, the number of threes. And then we can make the table because we were asked for the probability distribution. So our random variable here will be x. This is a six-sided die that we're throwing, and we are throwing it right here 4 times. Alright, so how many threes could we possibly get? Well, we can certainly get 0 if we throw the dice 4 times. So 0 is a possibility, 1 is a possibility, 2 is a possibility, as is 3, and 4. Now we can't get 5 threes because we're only throwing the dice 4 times. Alright, so that's the first column. Let's look at the next one, the probability that x equals x. So this binomial distribution, there are, we're saying that they're going to be, well, let me start down somewhere in the middle here and then we'll kind of work our way backwards. In order to do a binomial distribution, this is saying that we're going to have 2 successes. So we are going to have 2 threes when we roll. Well, we can do that choose 2 different ways. So that's the number of different sort of ways we can have the arrangements. In fact, maybe I should write out the formula here for a binomial distribution. It looks like this. Probability that x is equal to x is just equal to n choose r. This might be helpful. Times p, which is the probability of success, to the r times q to the n minus r. Probably should have started with this. So this is the probability of success. This is the probability of failure. This is the number of successes. And these are the number of failures. So here's our 4 choose 2. We have 4 different experiments that we're doing, or 4 trials that we're doing. We want 2 successes. I didn't say that here, but this is still the number of successes. Obviously, R here and R here have to be the same. So we want 2 successes. Our probability of success. Now, if we're going to roll a 3, our probability of success is 1/6. Oh, let's try that again. There we go. To the number of successes. Well, we're going to have 2 successes. And our probability of failure is just 1 minus 1/6, which is 5 out of 6. And we're going to have 2 of those. So everything's going to stay the same basically, except for these numbers right here. This number will change, this number will change, and this number will change based on where we are in the table. Everything else is going to stay exactly the same. So let's fill in the rest. Here we'll have 4 choose 0 ways of getting a success. 1/6 is the probability of success to the exponent 0 since we have 0 successes. 5/6 here to the 4 because we have 4 failures. And we just keep filling in the table from there. 1/6 to the 1, 5/6 to the 4, 3. You can see why a spreadsheet would be useful here. We're doing a lot of the same things over and over again. Whoops, that's a bad looking 6. This just a spreadsheet will save a little bit of time. Whoops, this is 5/6, and we want 1 of those. And our last one here, 4 choose 4, 1/6 to the 4, 4 successes, which means that we have 0 failures. Alright, and then we would go through and actually, I should maybe, before I do that, write out the answers here, and maybe a decimal equivalent of those answers. We could leave it as a fraction if we wanted to, but I think for just ease of use here, I'm going to turn this into a decimal equivalent of the fraction just to make it easy for us. So we'll call this 0.4823. I'm going to 4 decimal places. I'll explain why in a minute. This one here works out to 0.3858. This one is 0.1157. Here we have 0.0154. And the last one here, 0.008. So the reason why I went to 4 decimal places is that this column should add up to 1. These are all of the possible outcomes, and that was true back here too, is that this column, the probability column, should always add up to 1, sum to 1. And there was some rounding involved here, and if I didn't round properly, not properly, but because of the rounding I may have been off, but I think that gives us a total of 1. And then we would go ahead and do the XPX column that we have done before. Again, we're just going to take these 2 values, this one, and multiply them together. And we should get, let's see if I have those written down, something like this here, obviously 0 here. 1 times 0.3858 gives us 0.3858. 2 times 0.1157 gives us approximately, I thought I had those written down. I think 0.2, whoops, sorry, that's a bad looking 2. 2315. Next one would be 3 times 0.015 is 0.0463, and then the last one here should be 0.003. And now we can add all of these up to find the expected value, just like we did in the previous distribution. Or there's a shortcut here. When we're talking about the binomial distribution, the shortcut to finding the expected value is just n times p. I'll just write that in down here. E at x equals n times p. N is the number of trials, and p is the probability of a success. So in this case, we had 4 trials. The probability of a success was 1/6. So 4 times 1/6 would give us 4/6, which is the same as 2/3. Sorry for squishing this in here. I kind of ran out of room. So we can see that the expected number of 3s is 2/3. So not quite 1 3. If we were to do this experiment a whole bunch of times, we would see that on average we would get less than 1 3. In fact, we would get 2/3 of a 3 on average. Alright, so that's the binomial distribution, and the last distribution that we looked at was called the hypergeometric distribution. So this is when we conduct multiple trials. Should be an S in here. I don't know if I can fix that. multiple trials with two possible outcomes. So again, we're talking success or failure. The big difference with the hypergeometric distribution is that the trials are dependent. So one outcome depends on the previous one, sorry. So then there's a formula that we can use here. I often tell students that the easiest way to think about this is just think about this in terms of probability and combinations. So for example, here's the question. What is the probability of getting two spades if we take if 3 cards are dealt from a shuffled deck of cards? Now notice here we're going to deal 3 cards out. As soon as I deal out the first card, the probability of getting anything else from the rest of the deck changes because now I have one fewer card, in the deck. So these trials are dependent. So the fact that they're dependent means we're talking about a hypergeometric distribution rather than a binomial distribution. So what is the probability of getting 2 spades? So the probability that x equals 2. I should start out, I guess, by saying let x represent the number of spades. So the probability that we get 2 spades, well, how many spades are in a deck? There are 13 spades in a deck. We want 2 of them, and we're dealing out 3 cards, so we need 1 more card, and they have to come from all of the cards that aren't spades. 52 cards in a deck minus the 13 that were spades. 52 minus 13 gives us 40. So those are the desired outcomes. And then we divide by the total number of outcomes, which is 52, choose 3. Sorry, I almost wrote a 5 there. 52, choose 3, because we're choosing 3 cards from 52. And then we can plug that into the calculator and get a response. Oh, sorry, I just made a mistake here. I just realized that I subtracted incorrectly. 52 take away 13 is not 40, but rather 39. And so if we plug that into the calculator, we should get 13 choose 2 is 78. Sorry, bad looking 7. 39 choose 1 is 39, and 52 choose 3 is 22,100. And again, if we plug that directly into the calculator, we will get an answer of 0.14. So our probability of getting 2 spades when we deal out 3 cards from a deck of cards is 0.14. Now here things change a little bit. The question says, what is the probability of getting at least 2 spades? So the probability of at least 2 spades means that we're looking for the probability that x is greater than or equal to 2. So we're dealing out 2 cards. So that's the same as saying, hey, what's the probability that we get 2 spades plus the probability that we get 3 spades? Well, we've already done the calculation for 2 spades. We did it up here. And now we're going to do that calculation again for 3 spades. Sorry again for this being all squished. Kind of ran out of room. Well, the probability of getting 3 spades looks like this. 13 choose 3 times 39 choose 0. Whoops, 0 down here. Divided by 52 choose 3. And it turns out this is quite a small number. That part works out to 0.00011. So when we add these together, we get 0.1401, so 14.01%. And again, when we calculate the expected value, we could make a table like we did before, or there's a shortcut here, and the expected value for a hypergeometric distribution is just equal to the number of trials times the probability of A. In this case, the probability of A is the probability of a desired outcome. And our desired outcome here was getting a spade. We did 3 trials, and we wanted to get a spade, so the probability of getting a spade was 1 out of 13. So we multiply those together and we get 3/13, which works out to approximately 0.23. So again, on average, we would expect to get 0.23 of a spade. I know it's less than 1, but obviously when you're dealing out 3 cards, you would expect on average that you're going to have less than 1 spade. All right, so that was a summary of probability distributions. Hope that helped. Sorry, it was a bit on the long side, but I hope that helped.